Okay, so we'll start with the conceptual questions. And if you have any questions, just shoot me, let me know. Number one, we have an object being pushed to the right with a constant velocity. What is the value for the net work done on the object? The net work on the object is 0. And the reason why we know the net work is 0 is because it's pushed with a constant velocity. If the velocity stays constant, it's not accelerating. Okay, so then there's no net work being done on the object. You're pushing it to the right, you're doing work. There might be friction doing work against it, but the overall value for net work is 0 because the velocity is constant. Power and time, they are inversely related because it's power is work over time. So if the amount of time to do a task decreases, that means you need more power to perform the task. And then vice versa. If you get more time to do a certain task, the amount of power required decreases. So they are inversely related. One goes up, the other goes down. 3, energy based on motion, that's kinetic. 4, potential energy is stored energy that is ready to be used later. You can store potential energy in a multitude of ways. The 2 we talked about was potential energy due to gravity, which is based on the object's height. And the other one was potential energy based on elasticity. That's like a rubber band stretching or a springboard stretching. 5, why does an object thrown into the air have no kinetic energy at its highest point? If you were at your highest point, your velocity is 0. And we just said about number 3, kinetic energy is the energy based on motion. So if you aren't moving, you have no kinetic energy. 5, a ball is rolling across a table that is parallel to the ground. Is gravity doing work on the ball? Explain. Excuse me. So gravity is not doing work on the ball. And the reason why gravity is not doing work on the ball is because the table is parallel. So we have something like this. Here's your table. Here's the ball. Say the ball is going this way. Okay. Well, the force of gravity is going this way. There is no component of the force of gravity that is helping propel the ball to the right. So whatever's doing work to the ball is something, but it's not gravity. You cannot do work to something if it's perpendicular to the force being applied. All right, so gravity does not help something move parallel. All right. 7, a task takes a certain amount of power to perform. If the amount of power is doubled over the same time period, how much work can be done? Okay, so that's, again, looking at this equation. Okay. So it takes a certain amount of power to perform some task. If the amount of power is doubled, so if P goes up by 2 times and T stays the same, then work would also have to increase by 2 times. So how much work can be done? Twice as much work. Power and work are directly related. Whatever power does, work will do the same or vice versa if time stays constant. And then last but not least, if an object has its velocity tripled, by how much does its kinetic energy increase? And it is 9 times. So the formula for kinetic energy is 1/2 mv squared. All right. Ignore the half, ignore the m. It's v squared we're looking at. So let's do it like this. If v equals 1, all right, then v squared is also 1. Okay. If we triple v equals 3, then v squared is now 9. So however much the velocity increases by, you square that amount, that's how much the energy will go up by. So if you doubled the velocity, you would quadruple the kinetic energy. We tripled the velocity, so the kinetic energy went up by 9 times, and so on and so forth. So that's the 8 review questions. Any questions on these 8 questions?
Can you go through 1 through 5 since I missed them?
Oh my God, ridiculous. Sure.
Sorry.
1 through 5, we can do that. Anything else?
No.
All right. Okay. So 1, again, the network is 0. Again, the network. So really, if we draw it out, we're pushing some box to the right. Okay. So that's, the pushing force. But the velocity is constant. If we know the velocity is constant, that means there must be some other force acting in the same direct or the opposite direction. These have to be the same. If they're the same, then the net force would be 0, and we know work equals force times distance. All right, or work equals mad. F equals ma. So if A is 0, then there is no work done. The key thing to tell you again is constant velocity. That means the net work has to be 0. 2, power and time are inversely related. Right? Power equals work over time. So if P goes up, that means the amount of time required goes down, and vice versa. If you get more time to do something, the power requirement goes down. They are inversely related. 3 is kinetic energy, and 4 is potential energy. And 5, when you are at your highest point, you aren't moving, and we said kinetic energy is the energy of motion. So if you have no velocity, you have no kinetic energy. So that's why at your highest point, the kinetic energy is 0. Any questions about the front 5 or the 8? All right, so go like this. And then we'll go back to this. All right, so let's look at these problems. All right, and I know they were kind of tough. Some of them were definitely tough. So a person pulls a 5 kilogram box 10 meters forward at a constant velocity. Friction is 0.32. How much work is done by the person? So, if, again, here we go, constant velocity. So that means the net work is 0. So whatever work friction is doing, the person is doing the same exact value of work, just in the opposite direction. So we can actually solve this out of order. We'll solve B first. What is the force of friction? So friction is mu mg, 0.32 times 5 times 9.8. Okay, and that gets you 15.68. To find the work of friction, it's force times distance. So it's 15.68 times 10, and you get 156.8 joules. So one of these answers is the answer to how much work the person is doing. And then what is work done by friction? It's the exact same value, it's just the opposite sign. It actually doesn't matter if you make the first one negative 156.8 and the second one positive 156.8, or as they're listed here, where they're both, it's the way you're moving is positive and the opposite way is negative. For C, what is the net work done in the box? Well, if both works are identical in value, just opposite signs, then the net work is 0. And again, we know the net work is 0 because the velocity is constant. And then to find out if it was 30 watts of power, how long did he pull it for? So that's P equals work over time, or power equals 156.8 over t. And then remember, you can just trade these two values. T jumps to the 30 jumps to the t, and when we divide, you get 5.23 seconds. That was number 1. Any questions on 1? All right. Okay. 2. So we have a car, it starts from rest, it hits the gas, applies a force of about 120 newtons over 80 meters. How fast is the car moving after the 80 meters? All right. So we are going to need to find out how much work is done, all right? Because we're going to end up using this. Work equals delta K E. Work equals the change in kinetic energy. So to solve for work, that's just force times distance. So that would be 120 times 80. And that's going to get you 9,600. Okay. Delta KE is the change in kinetic energy. So it's the final kinetic energy, energy of motion, minus the initial kinetic energy. Well, the final kinetic energy is 1/2 mv squared. So 1/2 times m, which is 500, times v squared. The initial kinetic energy is 0 because the car starts from rest. So if we just use this, we can rearrange. This becomes 250, half of 500. Divide both sides by 250, and you take the square root. And if you round, I know it says 6.2. I think it gets you something close to that. Yeah, 6.19, 6.2. So that's letter A. That's how we solve the first part. To do the second part, just gonna write this up here. Okay, so now the car is losing 15% of its energy due to friction. How far will the car make it up the hill? So this is now a conservation of energy problem. So in the beginning of this problem, it kind of looked like this. We went straight. That's a terrible straight line, but imagine that's straight. And then we hit a hill and, oh my God, let me just start over. Okay. We went straight-ish and then up. So this part, the car starts V0 and then it ends here V6.2. So that's part 1 of the problem. In part 2, V0 is now 6.2. And we're going uphill. So we're going to stop. When does the car stop going uphill? It stops when V in part 2 is 0. So this is going to be a conservation of energy problem. The initial part starts down here in the green with a 6.2, and then the final part is up here. So we can build an equation that's going to look like this. In the beginning, we have kinetic energy, okay? But we also have some force of friction that we're going to lose energy from. So minus the work of F. Okay, that's the work of friction. And then at the end, when we're here, we're going to be some height above the level, above the ground. So H is something. That's the height we're looking for. So there's going to be potential energy on the right-hand side due to gravity. So in the beginning, we're moving, so that's kinetic energy. We lose some of that energy due to friction. And at the end, all of our energy has been transformed to gravity. Are we okay so far? All right, so we know the kinetic energy, we already found it. We don't have to rewrite it as 1/2 mv squared. It's 9,600. Right. we're losing 15%. So the work of friction is 9,600 again, times 0.15. That's 15% of 9,600. We're going to remove that. And we're going to set that equal to PEG, potential energy due to gravity, mg h. So 509.8 times h. So when we solve, if we do 9,600 minus 9,600 times 0.15, we get 8,160. And then 500 times 9.8, that's 4,900. H, divide both sides by 4,900 and you get 1.68 meters. Okay. Any questions? Question, Marion, or just waving your hand? Okay. You doing all right, bud? Yes or no? Okay. All right. All right. Three. Three was really brutal. Three was really, really hard. So if you had trouble with three, don't sweat it at all. So a 50-kilogram bungee jumper starts at rest on a bridge that's 68 meters in the air. The unstretched length of the cord is 8 meters. When falling at a height of 15 meters below the bridge, they're moving at 7.3 meters per second. What is the value of the spring constant, or what's the value for K? Okay, so definitely a conservation of energy problem. So in the beginning, we have a bungee jumper, right? Oh, there we go. We have a bungee jumper. They're on top of a bridge. All right. So in the beginning, they have potential energy due to gravity. Okay. That's all they have in the very beginning. Okay. So this is before they jump. Okay. After, okay, now the person is somewhere down here. Right? They're not at the ground yet, but they're falling down. Well, they actually have potential energy due to elastic at this point because the spring is starting to stretch. They have potential energy due to gravity at this point because they're still in the air. They haven't hit the ground yet. And they're moving, so they have kinetic energy. So they have all three forms of energy afterwards. In the beginning, it's just potential. So if we write our equation, it would be PEG equals PEG again, plus PEE, potential energy gravity, potential energy elastic, and kinetic energy. Okay, so if we plug everything in, this is going to be 55 times 9.8 mgh times 68. Okay. Potential energy due to gravity on the second part, again, it's mgh, it's 55 times 9.8, okay, times, well, they've fallen 15 meters, so 68 minus 15, that's 53. Okay. Plus, I'm gonna rewrite this, I'm gonna do kinetic energy next because we know everything here. That's 1/2 m v squared. Okay. Plus, potential energy elastic is 1/2 times the spring constant, that's what we're looking for, K, times x squared. X is how far something has stretched. So here's that part where it says think in the problem. The cord, so the person has fallen 15 meters, but the cord is 8 meters long without stretching. So like the cord by itself is already 8 meters long. If the cord is 8 meters long, it hasn't stretched yet. So the distance isn't 15, it's actually 7. right? The first 8 meters, nothing happens. The next 7 meters, that's where the cord actually starts to kind of expand like an accordion out. So this distance is 7 squared. So that's just like a bucket of algebra, and we just have to kind of go through all of it. So on the left side, these are just really big numbers. This is 29,645. Okay. 55 times 9.8 times 53. This is 28567. Oh my goodness. Seven. I know it's exhilarating. 7.3 times 7.3 times 50. 1465. And then finally, half of 49 is 24.5 times K. So if you combine these two terms and then bring them over to the other side, okay, and then divide by 24.5, you get 270.18. And then K's units are newtons per meter. Okay. Any questions about this first part? Okay. Don't worry about part B. You're missing information, I realized afterwards. It's not really possible to solve. So don't worry about part B. So we'll just ignore that part. And then last but not least, 4. So a skier starts at rest, 45-meter hill, 45 kilograms. All right, so here we go. So we have our picture. So in the beginning, they're up here. All right, they are at rest. So all of their energy in the beginning is potential energy due to gravity. All right, this problem is looking at the first part halfway. Well, at halfway, they're going to have potential energy due to gravity still because you're not at the ground, and they're moving, so there will be kinetic energy. So we start with potential energy due to gravity, which is mgh, so that's 45 times 9.8 times 45. Okay, but we lose 6150 on the way down, so minus 6150. That is the initial values. And then at the halfway point, that's what we'll do in orange. Okay, so it's mgh again, potential energy to gravity, 45 times 9.8. But not times 45. They're halfway down. Half of 45 is 24.5. All right, no, it's not. Half of 45 is 22.5. Okay. Plus kinetic energy, 1/2 mv squared. Okay. So if we solve the left-hand side, so 45 times 45 times 9.8, and we subtract 6150, this is 13,695. Okay, and then on the other side, we have 45 times 9.8 times 22.5. This is 9,922.5. And then plus 22.5 v squared. So we can subtract that 992 number over, divide by 22.5, and then we'll just take the square root, and you get 12.948, or as I put there, 12.9. Any questions about the first part? Okie doke. All right. So we don't need to erase all of this. All right, so in part B, problem starts off the same way, so we'll leave the part in blue alone. But now what we're looking at is at the very bottom, they lost 25% of their energy. How much do they have? So now way down here, since they're at the very bottom of the hill, the only energy they have is kinetic, okay? So what we can do is we can kind of look like this. We have 45 times 9.8 times 45. Let's quickly just solve what that is, just so we have a number. This is 19,845. Okay, so that's the initial energy we have. We're losing 25% of that. So that means we have 75% of our energy left over. So if we find out what 75% is of that, 14,883. Right, that now becomes our initial energy at the top. Right, so we have 14,883.75. So that's how much energy we have. And at the end, we set it equal to kinetic energy, 1/2 mv squared. So 1/2 times 45 v squared. Okay. So again, divide both sides by 22.5. And then we take the square root of 661, because that's what you get. Oh, and I went the wrong way. I did it again. 25.7. 25.719 or 25.7. Okay, so if he's moving at the speed at the bottom and the coefficient of friction is 0.33, how far will he move before coming to a stop? Okay. So here's what we know. So we know he's moving at 25.72. So now we can look at this. Work equals delta KE. Work equals the change in kinetic energy. We used this from before. So initially, we know the value for work, it's 14,883.75. It's this right here. And we know at the end of the problem, he's coming to a stop. So there is no kinetic energy at the end. So the work, okay, is negative 14,883.75. And the negative sign doesn't really matter. It's just negative because it's working against us. Okay. We want to find out the distance. We know work equals F times D. Okay. Well, we know work already. That's W. We got that right here. What's providing the friction, or sorry, what's providing our force? Friction. So to find FF, so to find F, it's mu mg, 0.33 times mass, which is 45 times 9.8. All right. So if we solve for F, 0.33 times 45 times 9.8, you get 145.53. That's F. So now we can do this. Work 14,887.75 equals friction 145.53 times distance. Now we'll just divide. Divided by 145.53, and you get 102. I got 102.3 meters. A little different than the answer I wrote down. That's a rounding thing. So I know these problems are difficult, but they basically encompass everything all at once. So yeah. Any questions on any of these problems? Okay. Well, if you have anything else, let me know. All right. definitely ask, send me a reminder, anything like that. I'll post this on YouTube as well, so you guys can look at it again. And it's not gonna come down during the test. Because that, I don't know how to do that, so. All right, anything else?
So what's going to be on the test tomorrow?
Nothing, everything's on Friday.
Oh,
I decided to change it to make everything on Friday because some people have to work today late and they won't be able to get to see the review till late tonight. It's not, I don't want to make them cram for it. So don't worry about it. The whole thing will be tomorrow and it'll be like the last test, it's just in one day, but there'll be some multiple choice and then a couple open-ended questions. And then just like before, you can send me your work via Remind. So in case there's a mistake, I can go back and take a look at it and give you a partial credit.
okay.
All right. Anything else? Well, I miss you guys. I hope to see you guys all in September. I'll be in my same room. You guys can come and bother me.
Okay.
All right.
Okay.
All day except for one day I'm in D Haas's room. Or one period I'm in D Haas's room. But feel free to bother me all the time. All right.
Mhm.
Luca, not to blow up your spot, how do you think you did on the AP test?
Good. Maybe like a 4. I don't know.
You think you did good?
Yeah, the first question was kind of rough, but the second one was easy.
Awesome. I'm glad to hear. Glad to hear. All right. All right, guys. Well, again, hit me up if you have any questions. Stay safe. Enjoy the nice weather today. Stay inside. It's gonna be hot out. Air conditioning is awesome. At least you're not going to sweat in school and stick to the bench. So there's that. Okay. There's that. Bye.
Thank you.
Bye.